additional tunnel via our watch back to the medical professional. We now have a secure tunnel from this machine, which is in a random gym somewhere in the world, to our own private doctor. Once we have that tunnel, and only when we have that tunnel, can we actually create a symmetric key, which we will use to pass the data. So it is all about the keys. It's all about how we set up the private tunnels and how we pass information. Now, of course, we then bring that back to Synergy itself. So we're using asymmetric key generation up here, the true random number generators and secure storage, and the unique identifier to create this session. At this point, we're going to use some asymmetric acceleration to pass these across, some secure storage, unique ID, transport layer security, and the crypto lib to pass information through the tunnel. And in this last part, we're going to use everything apart from the key generation to accelerate our application. The interesting thing is, we have created an incredibly high-value, differentiated application out of the same piece of silicon. Never before have we been able to identify a person on a random piece of gym equipment in a random gym and pass that back to our doctors without having to share that same information with the stakeholders in the gym manager, the person who owns the machine, the person who does the particular maintenance. I don't want my personal information going to everybody. I only want my personal information going to my doctor. So we're developing the capability for a brand new set of applications, but it is of this level that you have to think about how the keys are going to be passed and how we're going to manipulate these things.
So does it have a length of time?
The question was, does the session have a length of time? And you should rotate keys relatively well, but no, there's no real absolute number on that. So integrity is critical as well in here. Traditional embedded systems were not connected. So Synergy has been enabled to develop this root of trust, device personalization, protected memory, management of certificates, and secure boot. We also have the JTAG key in here, so the 128-bit debug access key. Roughly it'll take a billion years to crack that. Social engineering notwithstanding, if you set it all to ones, or you set it all to zeros, it takes less time. You'd be surprised. So that's fine. In terms of securing memory, the memory protection units are really important. Memory protection units are a key differentiator in the Synergy devices. So we have here the existing Cortex-M1, we have the busmaster and busload, and then we have the secure memory protection unit as well. This allows us to isolate different components away from each other. So again, if we look at secure manufacturing, the application that we showed on the expo floor here, we can personalize keys and send them through a secure mechanism to the manufacturing. We can encrypt the application. We can send those keys through, we can validate, and then we can program them. Again, in this sort of session, we need to limit the debug, we need memory protection, we need asymmetric keys, and lots of the other functions create this type of application. Safeguarding availability is also really critical. Here's an example I like. So again, from personal experience. And forgive me if you've heard this one before. So my other child was born premature. 7 weeks. He was very small. So we had to have him connected to a monitor for about the first 12 weeks of his life. And that was great, apart from he never got any sleep because the monitor kept going off. Today, thankfully, we're seeing more and more devices, but what would be great is if we could connect that type of device to other systems in our smart home. So connect it with the lights and with the alarm clock so that we wake up if the baby stops breathing, and the lighting between our room and the baby's room all come on automatically. The interesting thing here is we've taken 3 very disparate, extremely useful types of devices, and we've created potentially the most critical alarm system you will ever own as a parent. So we can start developing new novel applications. Now we can also send data out and to the Bluetooth. If we can get security right, we can then also start adding value. We can send the data out perhaps to the physician again or to the doctor. We can bring in context such as the weather report. The challenge that we have is as we build more and more devices, how do we manage those? So again, application support from the OEM and home monitoring. So we're building, again, lots of devices in the IoT which need to connect. And they need to have security between them. They need to be trustworthy information sharing. And again, we go back to the key exchange mechanisms that we were talking about earlier. Availability is really important. If we look down at the baby monitor, for example, there's a set of things that may become infected. IoT system behavior and communications can become affected. Whereas the sensor, configuration, and alarm, we want these to become completely inviolate. We don't want those to be harmed in any way. So again, with Synergy, we can separate and we can isolate these different components from each other. And we can do this using the memory protection units to create a robust secure boot underneath these ones. We can contain these inside the supervisor mode and these ones inside the user mode, so we have a layer of separation. I think I've run over time, so apologies for that. Synergy, very extensive, very easy to use, very powerful, and ultimately very, very secure. So security is not an afterthought. Cryptography is not sufficient on its own. We have to think about this in a wider context. And we need to leverage the right tools and industry best practice to achieve this. Okay, apologies, I ran a little bit over there. Do I have an hour? Okay, we've got plenty of time for questions. There we go. I knew I was bang on time. So, fabulous. Okay, so thank you very much for that. Hopefully it was useful. Are there any questions?
You talk about using apps to verify integrity, and my understanding is you want that to be an app. The page call is required to check separate to the event use for the encryption.
So the question is, when you're doing the Mac, or you're looking at the integrity of should that be a separate value? Yes, you do want to manage that, and you do want to manage the integrity over the long term as well. Okay, sorry.
Just on earlier, I asked about the 250 million vaccination.
Yes.
How many sources are there? Do you have an estimate of?
It's a good question. So the question down the front here was, as the 250 million attacks that we spoke about earlier, where are they coming from? It's difficult to put a number on. I haven't seen an exact breakdown. It depends very much on the types of industry that people in. The more heavy industry, they tend to be nation-sponsored. We're seeing a small but growing number of cyber-criminal type attacks, so ransomware and things along those lines, and then there's the occasional drive-by as well.
So, are we talking about like thousands of attackers during this meeting here?
So the question was, are we seeing thousands of attackers developing these attacks? I think it is a large number. I think obviously, again, it depends on the exact domain, but some attacks come from a very narrow set of attackers, nation states, but other ones are very broad. And there's a lot of people trying to break this, as we've seen with the automotive stuff. You know, there are universities, there are people who are doing it for financial gain, there are people just trying to do it to break things.
One of the questions is how much you mentioned manufacturing. So you have a certain product, some product. Against the Renesas key in this case to prove that it is a right device, and then you can pull that out. You can either do that and say, okay, well, I'm going to apply that to all Renesas devices. That's fine, it's perfectly possible. Or you can say, okay, well, here's a range of identifiers which I will allow it to update to. So compile once, deploy many times, again using the asymmetric keypad. What you do have to have is a secure tunnel to get that key manifest into the device so that you can then decrypt the application, the update on chip. No, they wouldn't. So the question was, on the running machine example, would they all have to have the same peripherals? Absolutely not. I think all that you would need is the ability to, in effect, inject your key information through again an encrypted link, and then that would allow that machine to communicate whatever data it has back to the medical professional. So that could be a different manufacturer, it could be a different way. Of course, the application side of it would need to mesh up, but the peripheral set wouldn't necessarily need to. Let's talk about the need for high-quality entropy and key generation. I wondered, what are the other standards for measuring quality of entropy, and where are those? That would be a broad opportunity.
Yeah.
Has the Synergy platform a standard for quality of entropy, the CMOS standard?
Yeah. So the question there was the level of entropy, how do you measure it, and are there standards around that? There is the NIST
standard, which I pointed to, so the 980 standard, and there is the A, B, and C, which is evolving on those. So with Synergy, we adhere to that, we adhere to the leading edge of that specification, and that, there are a bunch of papers. If you go to NIST, you can read about it. Any others? Okay.
API range over 30 bit. So you want to generate over 28 bit each, 4 times in a row, 28.
The 50 images are pointed to, so it's in the paper. Okay, we're out of time. Thank you very much. They're responsible to tell you details in a short way. Okay, so let's start with the original problem. Yeah, so this the whole talk is about the Kakeya problem. So you might think that poor gentleman is Kakeya, but no, he's Letikovic, because Kakeya didn't do too much, except asking the following problem, which is now called Kakeya needle problem. My handwriting is quite awful, so if you cannot read something, it's not your fault but my fault, so please let me know something you cannot read. So Kakeya had this almost 100 years ago, in 1917. Now this is the last thing he did, essentially, about the whole stuff. So his question was the following. Okay, so first I tell you and then I ask. So we have a needle like this, in the plane, and we want to rotate it 180 degree or 680 degree, and we want to do it so that the total area which is needed is the smallest. So let me write it more precisely. So we ask what is the minimum area of region in which a needle of unit length very complicated to turn around, and then the area pi over 4, which numerically 0.785. Okay, any idea how to improve this? Yeah, I like teasing students, so give me something. Or is it a map? Yeah, okay, so it's easier for you because you saw the picture. Okay, let's do something, something convex. So, Kakeya also, maybe he meant the question, what is the smallest convex? And I can show you the smallest convex. The smallest convex is a very tricky region, which is a regular triangle. Of course, the side length shouldn't be 1, because then you cannot do anything, but this is 1, the height is 1. If the height is 1, then of course you can easily do the job, just this way, this, right? Okay, and then of course this side is 2 over root 3, so then the area is 1 over root 3, and this is 0.577, and this is the best convex construction. I mean, this is not to be the best convex region. It was proved by Pál, Hungarian mathematician, in 1921. So not much after the question, the convex things. I don't know what's the name of it, and that's how I can show you. Yeah, this object is better if you allow non-convex stuff, so it's something like this, and this area is pi over 8, so just 1/2 of the original one, so it's 4.393. Okay, as you can see how nicely this can move around there. Okay, and so it seems that Kakaya probably expected that this is the best one. Okay, so you saw this number, this number, this number. What is your guess? What can be the smallest area, roughly? Okay, so it must be between this and 0. So let me ask, who thinks that it can be less than 0.2? Who thinks that this is impossible? Okay, so there are more people here, so let's count this as well. Who thinks that we can go less than 0.1? Who thinks that we cannot? Okay, so it seems that this is somewhere where the guess is. Well, I don't know how natural these guesses are, but the answer is more surprising. The answer is that there is no smallest area, and this is what Besikovic did. So now let's go back to his face. Yeah. So this old gentleman wasn't old at that time. Okay, I'll be right 2 days. 1919, when he did something without, which at that time he lived in Russia, and he hadn't heard about this problem, and he essentially solved this. He was in England, in Cambridge, and then he realized that he can answer this question. So he said an arbitrary small area is enough. It's not hard to see that you cannot do it with 0 area, because if you don't get 0 area continuously, you cannot move anything. But you can make this area as small as you wish. Okay, and I can show you a possible geometric construction. It's not exactly what it is, but pretty similar. Okay, so the idea is, okay, so take a triangle. Of course, it's enough to rotate 60 degrees. If you can rotate 60 degrees with small area, then 6 times that will be enough. So in this triangle, I can easily rotate 60 degrees. So I can rotate it like this. Okay, there's a jump which I have to explain, and after the jump I can go on. But the jump is a parallel jump, and any parallel jump is easy. With arbitrary small area, this is what Tal joins. So if I have my needle here, and I want to move this needle here to this parallel segment, then I can do this arbitrary small area. Can you see why? Yeah, so I move it quite far, like here, and then I slightly turn it. So now I need this area, but the smaller the angle, the further I take, the smaller the angle. So then I move it here, and then again I rotate. So I need only these 2 areas, and these are as small as you wish. Okay, so parallel movements can be done very as small as you wish, and then we can keep repeating this. So now we decompose it into 8, and then every 2 move like this, and then they are moved like that, and we get like that. This is the so-called Perron tree. So this presentation, this construction used Perron. Yeah, sorry, no. And then we get something like this after some point. Yeah, beautiful picture. So you can see that there are these kind of. Okay, and to be honest, I don't understand too much from this picture either, but I think it looks pretty nice. So I leave it here. Okay, so the geometrical case and the needle problem, when we want to rotate the needle continuously. But if you somehow take the limit of this, so from this arbitrary small contraction, in the limit case, you get the following contraction, you get the set, and this is actually what Besikovic did in 1917. That he constructed a set, so Besikovic in 1917 constructed a compact set in the plane that contains unit segments in every direction. Okay, so if you don't want continuous movement, just segments in every direction, then you can make this area to be 0. And in fact, this is what Besikovic was interested in the question, if we have a, so his motivation came from analysis, that he asked himself if we have a function of 2 variables, and we know that it is Riemann integrable in the plane, whether we can always find a coordinate system, so that in that coordinate system we can take just the integrals in one direction and the integral then. And he realized that to show a counter example, he would need such a construction, and then he provided this construction, and then convinced himself that the question, this analysis question, is a negative answer. Okay, so this is the Smeltkowitz set, and this can be constructed using this Ferron tree stuff as well. But now I want to show you a completely different approach. Surprisingly, this is also due to Berkeley College, but about